Okay, we are going to look at part 2 of this, which includes p-value and confidence interval. So again, same section, we're just going to keep moving forward. So our objective, first of all, is to test a claim about a population mean with sigma known using p-value. So a p-value is the probability of observing a sample mean that is as or more extreme than the observed. We're going to compare the p-value to another value. The probability, it's a probability, is calculated assuming that the null hypothesis is true. That's the assumption we make in the classical approach as well. We use the p-value to quantify how unlikely the sample mean is. So we're comparing the sample mean to the population mean. Just like the classical approach, we calculate the test statistic z sub 0, which again is x bar minus mu over sigma over the square root of n. Formula did not change. We then calculate the p-value, or the probability the sample mean would be this, or more extreme, if the null hypothesis was true. Then a two-tailed, left-tailed, and right-tailed test calculations are slightly different. Don't worry, I'll teach you that. That's not hard to figure out. For a two-tailed test, the unlikely region are values that are too high or too low. Probability of being at this difference means the chance of being too far high or too far low, just like it was before. It's the tails, so anything that happens in the tails is problem. For the left-tailed test, the unlikely region are values that are too low, so only the low side, and it looks like this. The probability of being at this difference means you're over here. For a right-tailed test, where values that are too high, again, looks like this. It's the probability of being, that probability is probably too high. All right. So for all three models, two-tailed, left-tailed, and right-tailed, the larger p-value means the difference is not relatively large. The smaller p-value means the difference is relatively large. Now, what does that mean? Here we go. For a p-value of 0.3 means that this value or more extreme could happen 30% of the time. 30%, not unusual. Our unusual line is at 5%, but let's see what's going on here. Smaller p-values, a p-value of 0.01, for example, means that this particular value, or one more extreme than it, could happen about 1% of the time. Now, 1% is less than 5%, so this time it's unusual. So here's the decision rule. For a significance level of alpha, do not reject the null hypothesis if the p-value is greater than alpha. Reject the null hypothesis if the p-value is less than alpha. Look at that again, that's very important. Do not reject if the null hypothesis is greater than alpha. Reject if the p-value is less than alpha. Okay, for example, if alpha is 0.05 and a p-value of 0.3 is likely enough compared to 0.05, but a p-value of 0.01 is unlikely compared to 0.05. So here's an example of our two-tailed test. We've seen this before. Bolt manufacturer claims the diameter of bolts is 10, so we have 10 and not 10. Sample size of 40. Somehow we know the standard deviation is 0.3. The sample mean is 10.12, and the level of significance is 0.05. Do we reject? Let's find out. We do our math. We get 047 for our test statistic, or I'm sorry, 253 for our test statistic. Then it's a two-sided p-value. So we look up our p-value, and it's 0.01, which is less than 0.05, which is our alpha value. So our conclusion is we reject the null hypothesis. I know you're all sitting there going, where did that number come from? Hang on, I'll show you. Just give me a couple minutes. We have sufficient evidence that the population mean is not 10. Okay, here's an example of a left-tailed. Again, I'll show you how to find these. Just hang tough with me for a couple more minutes. Car manufacturer claims the miles per gallon of a car is at least 29. So equals 29, 29 or greater, and then less than. So we are on a left-tailed test. We have a sample of 40. Somehow we know the standard deviation is 0.5. So the sample mean is 28.89, and we have an alpha of 0.05. Do we reject? I don't know. Let's find out. So 28.89 is lower than 29, so we find the standard error, and our test statistic is the same as before. We look up our test statistic, and it turns out to be 0.08. 0.08 is greater than 0.05. 0.08 is greater than 0.05, so what do? We do not reject. So we have insufficient evidence, we do not have sufficient evidence, however you'd like to say it, that the population mean is less than 29 miles per gallon. Okay, here's a right-tailed test. Bolt manufacturer claims the defective rate of their product is at most 1.7 per 1,000. So again, H sub O and H sub 1. We have a sample size of 40. Somehow we know the standard deviation is 0.06. The defect rate is 1.78. And again, we'll use alpha as 0.05. And do we reject? Well, 1.78 is 0.08 higher. Standard error is 0.009, so our test statistic is 8.43. It's a one-sided test, and it's very, 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 very small that I would be 8.43 would have the probability. So our conclusion is we reject the null hypothesis. We have sufficient evidence that the population mean rate is more than 1.7. Okay, now I know you're sitting on our calculator, so you don't have to worry about finding the p-value, so hang tough for a minute. All right, so test a claim about a population mean with sigma known using confidence intervals. Okay, we all know how to find confidence intervals in our calculators, so here's what it's down to. The confidence interval approach yields the same result as the classical and the p-value. We compare a hypothesis test to a level of significance alpha to a confidence interval of 1 minus alpha times 100. That's where we get alpha from in the first place. And here's what it's down to. We do not reject if our mean is inside our confidence interval. We reject if our mean is outside the confidence interval. The hypothesis test calculation and confidence interval calculation are similar. You know how to do confidence intervals on your calculator, so no matter what it is, you already know how to do that. So we'll talk about those we'll do problems in a few minutes, I promise. Okay, here's an example. We're back to that bolt. Okay, two-tailed test. We have a sample of 40, 0.03, everything's the same. Do we reject? Well, we find a confidence interval. Again, we practice this on our calculator. So we have 10.12 plus or minus 1.96 times 0.047, which leads to 10.03 and 10.21. Is 10.0 inside or outside of our interval? It's outside, so we reject the null hypothesis. We have sufficient evidence that the population mean is not 10. I believe that's what we got just a few minutes ago. All right, left-tailed test. We're back to that car. There it is. Same information. Same information. So do we reject? Well, we have 28.89 plus 1.645 times 0.079. We only need the top end because we're doing a right-tailed test. So we only need to know, is it inside our interval? It is inside our interval. So we do not reject the null hypothesis. We have insufficient evidence that the population mean is actually less. So we're good. It did fall inside, so we failed to reject. Good job. All right, here's a right-tailed test. Bolt manufacturer, defective rate, same as before. Same information as before. We calculate the confidence interval, but this time we only need the low side. We only need to know if it's going to be in here or not. And 1.7 is not inside our interval because our interval starts at 1.76. So we reject the null hypothesis. We have sufficient evidence that the population mean is actually more than 1.7. Again, this is a process. If it's inside the interval, we keep it. If it's outside the interval, we reject it. All right, last thing. What's the difference between statistical significance and practical significance? Just a little. So, don't stress out over this. Just because we say it's statistically significant doesn't mean that in reality we should throw out the baby with the bathwater. So hang tough with that. We are in good shape. Okay, that's the end of our notes. I'm going to slip over and make another video to get you started on some, get you started on some problems. Give me a second here to get out of this.